Alright, so today we did transformations, we did absolute value and quadratic functions only today, and we did transformations with h and k. So the first thing I want to point out is our h and our comma k is going to be our vertex of our new function once we transform it. So we're going to have a general function and we're going to add an h and a k to it and see how it moves. So if we have, and I messed up these notes, but if h is greater than 0, so if h is positive, then we are going to move to the left. Okay, so if we have y equaling the absolute value of x plus 3, we're moving the opposite way, so we're going to move left 3 units. Okay, if we have a h that is less than 0, so if our h is negative, so if we have y equals x minus 4, we're going to move 4 units right in the positive direction. So h is kind of opposite of what it's saying. Then we have k. If k is greater than 0, so if k is positive, we move up. And so if we have y equal absolute value of x plus 3 on the outside of our parentheses, or in this case our absolute value, see the difference? This is on the inside, this is on the outside. This is h, this is k. We move 3 up. If our k is negative, we have x minus 4 on the outside, we move 4 units down. Okay, so looking at this first example here, we have the absolute value of x plus 5. So we have nothing on the inside with x, so h is 0, we have no h. We have k on the outside, that is a positive 5. So our transformation is going to be moving up 5 units. Okay, and our vertex is going to be our h comma k. So our vertex is going to be 0 comma 5. So we can go ahead and plot that even. And I would do the table of values next and then work with this. So we can have a table of values x and y. I'm fine with just doing 3 values and plugging that into the function. So when we have the absolute value of negative 1 plus 5, we get 1 plus 5, which gets us 6. When we have the absolute value of 0 plus 5, we get 5, and the absolute value of 1 plus 5 gets me 6. So we already plotted our vertex, and then we plot 1 comma 6 and negative 1 comma 6. And we make sure that we remember the shape of our absolute value function is always a V, so the lines are straight. Okay, our domain in this function, moving left to right, our x values are going to be negative infinity to positive infinity. It's going to touch all of the x values because these are going left and right. Our range goes from our lowest y value, which in this case is positive 5, all the way to negative infinity because they're going up. Okay. Our x-intercept, it does not intercept our x-axis, so we have none. And our y-intercept is at 0 comma 5. Write this as an ordered pair. Always. Okay? And if you wanted to compare it to the parent function, back from what we did yesterday, our parent function starts at the vertex and then goes out. So we can actually see the transformation of this compared to our parent function of just absolute value of x. Okay, so that's how that changed. Going to this example, we have the absolute value of x minus 2. So in this case, h equals 2 and k equals 0. Okay, so h is positive 2 because remember we are moving the opposite direction when we are looking at h. Okay, so our vertex is going to be 2 comma 0, and our transformation is going to be right the opposite of negative, so positive 2 units. So we're going to be over here. We can make our table of values. So we'll have, let's do 0, 1, 2, and 3. We need to start with 2 because this is our vertex. Okay, so we need that in there. So if you want to start with your vertex and do 1 up and 1 down, that's totally fine with me. Or 1 down, whatever. And then we plug these into our function. So the absolute value of 0 minus 2 is the absolute value of negative 2, which is positive 2. Then we have the absolute value of 1 minus 2, which is the absolute value of negative 1, which is 1. Then we have the absolute value of 3 minus 2, which is the absolute value of 1, which is 1. Then we plot these, so we have 0, 2 already, or sorry, we have 2, 0 already. We also have 0, 2, 1, 1, and 3, 1, and we can connect those lines. And as we can see, it shifted to the right. Our domain is negative infinity to positive infinity. Our range is 0 included. Oh, and here 5 should have been included too. 0 included, comma, infinity. Our x-intercept in this case is 2 comma 0. It's where it crosses our x-axis, and our y-intercept is where it crosses our y-axis at 0 comma 2. Okay, writing the equation of a function with the following transformation. If it shifts 3 units to the right, we know that we are dealing with h. So shifting 3 units to the right would have to be on the inside, and it would have to be opposite. Shifting 12 units up would have to be on the outside, because we know that up and down is k. So we would have the absolute value of x plus 12. And we did quadratics. So same type of situation here. In this case, we have a quadratic function. So we know a quadratic when we see the square right here. And we have an h and we have a k. Okay. So our vertex, right, is h comma k. And in this case, it's going to be 1 comma 4, right? H is always opposite. So we know our vertex. Our transformation is going to be right 1 unit and up 4 units. So we can go ahead and go to the right 1 and up 4, and that's going to be our vertex. Okay. Making a table of values, I would always start with my vertex, and then I would go 1 this direction and 1 this direction. 0, and plugging this in, we have 0 minus 1 squared plus 4 gives me negative 1 squared plus 4, which gives me 5. And in this case, I have 2 minus 1 squared plus 4, which gives me 1 squared plus 4, which gives me 5. Okay. Then we can go ahead and graph these. So we have 0, 5, and 2, 5, and we know that it is a quadratic. Okay. Our domain is negative infinity to infinity, and our range is our lowest y value, which is 4 included, all the way to positive infinity. There is no x-intercept because it doesn't cross our x-axis, and our y-intercept is at 0, 5, where it crosses that y-axis. Okay, and then we have this example here. So real quick, we have our h, we have our k. Our vertex is going to be the opposite of h, k. Our transformation is going to be right 3 and down 6. Okay, so we do the same as this, the opposite of this right here. So we know our vertex is at 3, 6. We make our table of values starting with our vertex. Oh, that's supposed to be a y. I was thinking of 6. And we can go up. Let's do 2. Oh my gosh, I went the wrong direction. Let's do this. Wait. Oh my goodness. Let's do 3, 2, 1, 4, and 5. Gosh. Okay, plugging 1 in for x here is going to get me -2. You guys know how to do this. Plugging 2 in for x gets me -5. Plugging 4 in for x gets me -5. Plugging 5 in for x gets me -2. If you guys have not noticed a pattern already, these numbers that are sandwiching our vertex are going to be the same because they have symmetry about the vertex. Okay, so then we come and we graph these points. So we're at 5, -2, and we obviously had a big transformation there. Domain, still negative infinity to infinity. Range, our lowest y value included to infinity. The x-intercept, all right, so this one is almost, I would say, 1/2, 0, and we have another x-intercept, okay, we have 2 x-intercepts, crosses twice, at about 5.5, 0. Our y-intercept occurs at, real bad drawing, but let's say 0, 2. And lastly, writing an equation, shifting down is going to be k, left is going to be h, opposite. So we're going to have y equals, we know this is a quadratic function. Okay, so we have that x, that squared. We know that we're doing the opposite of left, so +4 and -12, down 12. Shifting 9 units to the right, we're going to have -9, and 1 unit up is going to be +1. So opposite of k, which is up and down.